Good day, grade 10s, and welcome to the first video on vectors and scalars. Today we would be looking at vectors and scalars, and we'll be looking at exactly what vectors and scalars are, different types of vectors, different types of scalars. You know, how is a vector drawn? And what rather we're going to talk about resultant vectors as well, and we're going to talk about different representations of vectors. Okay. So vectors and scalars is fairly a very short topic. So we shouldn't expect to do much in this topic, but we should expect to know a lot. Okay. So for starters, we define what exactly is a vector. Just do this. Let's try to. Okay. Hope you guys just saw that's like vectors and scalars, but anyway. So what exactly is a vector? So by definition, a vector is a physical quantity. It is a physical quantity. It is a physical quantity. It should be quantity that possesses both magnitude and direction. Both magnitude and direction. Okay? So look at a vector. We say that a vector is a physical quantity that has both magnitude, right? It should have both magnitude as well as direction. Right, so we look at different examples of vectors, right? So think about it. So I'm not sure, well, I know on my side that has never happened. I'm not sure about you, but on think of it this way. Has a situation ever occurred in your life where maybe perhaps you ask someone for the time at a specific moment, and they say to you it's actually 10 o'clock east, you know? It's like you've probably never had that before. Like, what's the time right now, bro? Nah, the time right now is like 10 o'clock to the right. This just doesn't make sense. Or, yo, bro, what's the time right now? Oh, what time did you wake up this morning? A bit late, man. I woke up at like 11 p.m. North. There's no such thing as time with a direction, right? So time is not an example of a vector. It is, however, an example of something different. So what would be an example of a vector? Well, with the vector for starters, we have what we call force. So what is force? Force, for starters, is measured in what we call newtons, denoted with the letter N, just a capital letter N, right? So force is an example of a vector. So for example, with force, we'd be looking at 5 newtons. Remember, newtons is the SI unit for force, right? So it's force. So force would have something like 5 newtons north, you know, 7 newtons, um, 7 newtons west, So it's the direction. Sorry. So it is 5 newtons north. So how do you actually look at this? So this would be your magnitude, and this would then be your direction. Similarly, this would be your magnitude, and this guy right here would be your direction. Hence, we say that force is an example of a vector. By definition of a vector, it is a physical quantity with both magnitude and direction. Okay, so if we look at the first one, which is force. So what would the second one be? So the second one would be displacement. So what exactly is displacement? There's a very common misconception with the definition of displacement and distance. Now I want you to note this. Distance is a certain path traveled, right? It is actually the total path that is traveled by something or an individual or something. It's just the total path traveled. So you would have maybe like a road, and on that road you try to get from point A to point B, right? So you would travel a certain distance, right? What would that distance be? So to get to point B, you'd be like, okay, so I want to get from this point all the way to that point, right? So that would be a certain distance, maybe 5 meters. That is distance. But if I want to ask myself, how long, or rather, how did I get from point A to point B, right? So it's like immediately from A and straight up to B. How did I get from A to B? I mean, the obvious answer would be, well, I walked from A to B. But then when we talk about displacement, we'd be like, okay, it should be the final point minus where I started. So it's like I started at point A and I ended at point B. So what would be my displacement? My displacement would then be the difference of the positions, meaning the difference of B, the difference of position B and position A. So you measure it from the start to the final position. So it would be from A to B would be my displacement. But if I had to determine what we call change in displacement, then that would be B minus A. But that's not what we're looking at right now. Okay, so I just wanted to clear the confusion between distance and displacement. Now remember, distance, it's the entire path that you've traveled. It is the entire path. But displacement is the difference between the start and the finish. So it's obviously you start at A, which would be no movement, so it's like 0 meters, and then let's say B is 5 meters from A, so B is 5 meters from A. What would your displacement be? Your displacement would be your difference. Remember, difference from mathematics means minus. So your displacement would be your difference from 0 to 5 actually. So that's what your displacement would be. It would be from 0, right? From 0, which was your start, to 5, which was your end. Not considering everything that happened throughout the entire journey. That would be distance. Okay, so displacement is another vector quantity. Vector. I'm gonna say vector quantity, and displacement is, well, we should know this. Displacement is measured in meters. Yeah. So looking at displacement, which is measured in meters, and we look at another one which we call weight. Okay. And weight is also measured in newtons, right? So weight is measured in newtons. Now, another very common misconception is between mass and weight. These two things, okay, are not the same. Why? Because when you talk about mass, we are talking about, let's say you go to the gym, and at the gym, your gym, I don't know what they call them. I've never been to a gym before, but you go to the gym and you have a gym instructor. I don't know if that's what they call them, or what do you call the person that actually helps with the weights? The the spot, something like that. So you go to the gym and they ask you, what do you actually weigh? What is your mass? You tell them, oh, my mass is 7 kilograms. That would not be a typical human's mass, by the way. Unless you're like really tiny. So my mass is 7 kilograms, right? Okay, let's just be a bit more realistic. 47 kilograms. So I weigh 47 kilograms, right? So that is mass. But when we talk about weight, we are talking about a type of force. So weight and mass are not the same thing. So if it means you need to say to your friend, well, you have gained mass. That is a proper way of saying it. It's better than how we say it in everyday life. Oh, buddy, you've gained weight. That is not the proper way of saying it. It is rather better for you to say, oh no, you've gained mass, because mass is the one measured in kilograms, weight is measured in newtons. Okay, just wanted to clear that. Okay, now we've looked at force, we've looked at displacement, we've looked at weight. Another final example of a vector would be velocity, velocity, and that is in meters per second. And someone else could have just done this. It's just the same thing, I mean, the moment I add this forward slash, there's no need for that. Okay, but yeah, it really doesn't matter how you write it as long as you write it correctly. So you have the velocity. I've been coming with a lot of these misconceptions, but with velocity, we compare velocity to speed. Ladies and gentlemen, please know that velocity is not the same as speed. Yes, they are both measured in meters per second, but speed, well, sorry, velocity is basically saying, okay, so when I look at my velocity, I'm looking at 10 meters per second east, you know, or to the east. And I look at my speed. With my speed, I am looking at 10 meters per second, right? So that is a difference between speed and velocity. Okay, cool. So we've looked at force, we've looked at displacement, we've looked at weight, we've looked at velocity, and I think the fifth one would be cool. Yes, acceleration, acceleration, acceleration. Yeah, that is in meters per second squared. Right. So these are the five vectors that you should know in grade 10. You need to be very familiar with. It's very important that you familiarize yourself with all of these. Yeah, it's very, very important. So what did we look at? We looked at what a vector is, and what is a vector by definition? It is a physical quantity that has both magnitude and direction. And we look at the other guy over here, which we call a scalar. So what is a scalar? A scalar, by definition, is a physical quantity. It is a physical, it is a physical quantity with magnitude only. So it only has magnitude. Yeah. So what are we looking at? Remember, with the vector, we had a magnitude and direction, but with the scalar, we only have magnitude. So what exactly would be a typical example of a scalar? Like I said, there's no such thing as 10 a.m. East. So obviously your first guess would be time. It only has magnitude. It can only be 11:30 and not 11:30 East. Okay? It can only be 11:30. I mean, think about it. Even when you're sick, there's no such thing as going to the doctor and they ask and they measure your temperature and the doctor says to you, oh bro, you are really sick. You are really sick. You have a very high temperature of 47 degrees Celsius north. I think just even saying it is very funny. So it's 47 degrees Celsius and that's it. There's no such thing as 47 degrees Celsius east or southwest or up or down or left or right. It's just 47 degrees Celsius. So that's the next example. We're looking at temperature. Okay, so the temperature. Another example would be the opposite of velocity, or rather the cleared misunderstanding of velocity, and that would be you got it, speed. Oh, sorry, I forgot to say this is measured in seconds, or it could be in. It really doesn't. Well, for starters, in physics, we always have our time in seconds, but time in general would be in seconds or in hours or in minutes, etc. But in physics, we generally just have it in seconds. Okay. So we have time, we have temperature, degrees Celsius, and another one which I'm not sure if you guys know, it's Kelvins, just Kelvins and degrees Celsius share a certain type of relationship. Okay, and then we have speed, which is also in meters per second. Right, so we looked at time, we looked at temperature, speed, and there's a fourth one. Oh, distance. Distance. Now remember, I've cleared the misunderstanding between distance and displacement. However, distance is also measured in meters. Okay, so we've looked at distance, and the fifth one would be mass. The fifth one would be mass, which is in kilograms. Okay, I think that's just about it for you guys. So you need to make sure that you know these. Familiarize yourself with all of these. You should be fine in the exam. Okay, so those are vectors and scalars. Now we're going to talk about the graphical representation of a vector. How do you actually draw a vector? So we're going to look at the graphical representation of a vector, right? How to actually draw a vector. Now, in order to draw a vector, you need to know this. Okay, for starters, a vector is a physical quantity that has both magnitude and direction, right? What you need to know is that a vector is represented by an arrow. Represented by an arrow, okay? And the scale, so sorry, it's represented by an arrow and it has its length. It's represented by an arrow and its length, which is equal to basically um, the size of the vector. So I refer to magnitude, and so your teacher could say size, but I really do believe she'll just use magnitude. But magnitude and size are basically just synonymous to each other. Okay, so we look at magnitude, and which is also called size. Right, so we say it's represented by an arrow, and its length is basically read as its magnitude. Okay, so whatever the direction of the arrow is, so the direction of the arrow, is basically here the direction of the arrows, basically the direction of the vector is the direction of a vector. So the direction of the arrow is direction of vector. Okay, so say for example, okay, now I need to draw my vector. Now remember, we say it's represented by an arrow. So I would have something like this. That's my arrow. I just like to shade it in. I don't know why. I just have that habit. It's just in me. Just it's always been there. Okay. And we would have our length, which will then be our magnitude. Okay. And we call this guy right here as the tail. And we call him the head of the vector. And we call this the tail of the vector, and this guy the head of the vector. Okay, so that's how we draw a typical vector. It's just an arrow with a head. And the head, what you need to know is that the head gives us the direction, right? It gives us the direction of the vector, and the tail gives us the magnitude or size, but please stick to magnitude of the vector. Okay, so this is how you draw a typical vector. And another thing that I want you to have, just a quick NB. NB is a very important point. You need to make sure that you choose a direction as positive. It could be left or right, you know, but I most typically just like to choose right. And even in my classes, I prefer my students use right as positive. So we take right as positive. I really prefer you do that. I would actually suggest that you always do that all the time. If you had to choose a direction of convention, then we'd just say right is positive, right? And that actually brings me to this. How to actually determine what we call the resultant vector. But before I get to that, let's just look at a few examples of how we would basically draw a typical vector and how we would actually read it, right? So for starters, let's say I have a vector like that in that direction and it's 7 newtons, okay? Um, okay, so how would I read that? So I would say that is a vector 7 newtons. Now look at the direction. It is to the right. So it's 7 newtons to the right, right? Let's look at a second one and let's say this is 2 newtons, and that would typically be 2 newtons to the right, right? And let's look at another one. Let's just take this one, and that would be, let's make that 4 newtons, and that would be that's 4 newtons to the right. You actually noticed the mistake. I did that on purpose because I knew that you were actually gonna realize it because you are very smart. Yes, it is 4 newtons to the left, right? So we have 4 newtons to the left. Why? Because the head shows the direction is to the left, is pointing to the left. It tells us that this arrow is, this vector rather, is to the left. So it's a vector of size 4 newtons to the left. Vector of size 2 newtons to the right. Vector size of 7 newtons, well, to the right. Okay, so that's how you draw a typical vector, So as I said in my classes, and I also prefer you do that. Wherever you are watching, I prefer that you always take your right as positive. Very, very safe. You play it very safely if you do that. I'm not saying it would be incorrect to take left as positive, but I'm just saying it's rather more efficient. Not sure if that's the right terminology, but anyway, to be more efficient to take right as positive. Okay. Now your convention really matters when we talk about what we call the net or the resultant vector. The resultant vector. Now, what is a resultant vector? By definition, I'm not going to write it down. It's a bit long, so I'm just going to say it out loud. So you have 2 definitions, right? So the first one is, I'm just going to write that as the first one and the second one, okay? So the first one is a single vector with the same effect as 2 or more vectors acting on an object, right? So that's a single vector. Sorry, that's just a little blunder. A single vector that has the same effect as 2 or more vectors together, right? Acting together, right? It's a single vector. So we have a single vector. This guy right here is a single vector with the same effect as 2 or more vectors acting together, right? And the second definition would be the vector sum of 2 or more vectors acting on an object. And mostly your teachers just don't prefer that. So it's just better to just stick to the first one. A single vector with the same effect as 2 or more vectors acting on an object, right? Or acting together. Okay, so what you need to know, very important points, you need to know, for starters, that the resultant vector, I'm just going to say res vector, the resultant vector is large or larger when vectors are in the same direction, And obviously the opposite is true. The resultant vector is smaller when vectors are in different directions. Yeah, that's a very important point. So what do I mean by that? I actually mean basically that if I had to take an example where I would have, okay, before I take the example, I just want to say this very important thing, another NB. Vectors in the same direction are added together. So you add them, plus sign. And vectors in opposite directions are the inverse of addition, which are subtracted. Cool. So that's what you need to know, that vectors in the same direction, we typically add them, and vectors in opposite directions are subtracted. Okay? It's a very important point. Um, right. Now we get to the deepness of this topic. Okay. So we say that vectors in the same direction are added and in opposite directions are subtracted. So what I mean is that if I had a single vector in that direction, and that's 5 newtons, and I had another vector in that direction, that would be say 2 newtons. If I had to determine my resultant vector, remember they are in the same direction. Look at the head, to the right, to the right. Therefore, that I then know that I need to add those two vectors. So that's 5 newtons plus 2 newtons, and that gives me 7 newtons. So what is the direction? 7 newtons to the right. Well, I knew it was to the right just because of the fact that both my arrows are to the right, right? Both of them are to the right. But another thing you could actually look at is the sign. Remember, you've chosen a convention and you have chosen right. So your convention was right, is positive. So obviously, if you have a positive answer, that means it's to the right, okay? You'll see how helpful that is in just a moment. So we've looked at 5 plus 2 newtons, that gives us 7 newtons to the right. So I had another thing. So you notice how I have my vectors drawn like this, right? So I have vectors in this way. So it's just so it's a vector on top of another vector, and just like that. This is how you actually draw vectors if those vectors are in the same direction, right? But assume we had vectors in different directions. Well, you need to make sure, rather, a very important point, that once you've drawn your first vector, your second vector must be drawn from the head of the first vector. Meaning if my first vector is 5 newtons, the head is right there. My second vector must be drawn from the head of the 5 newton vector. Okay? It's number one. So number two, let's say I have a vector here, and it's to that direction. So take 5 again, 5 newtons. And I have another vector in the opposite direction. Remember, I need to draw from the head of the first vector. So just fix that. So the head is this guy right here. So I'm going to draw from him. I'm then going to have it this way. So I'm going to say it's another vector in that direction. So let's make that 2 newtons, right? Okay, so what is my resultant vector? My resultant vector would then be, remember, we subtract vectors in the opposite direction. We subtract vectors in the opposite direction. So we're then going to say 5 newtons minus 2 newtons. And one would obviously say that's 3 newtons to the right. But that is wrong. That is not correct. Why? Like I said, you'll need to actually understand how important this thing is. Right is positive is very important. Because notice something. Once you realize that for starters, 5 newton, the 5 newton vector is to the left. Look at the direction, look at the head, which gives you the direction. It is to the left, right? And the 2 newton vector is to the right. So you notice that, okay, so that is 2 newtons to the right and 5 newtons to the left. What did you say? You said that right is positive, and obviously, if something is not to the right, it's to the left, and if right is positive, then left is negative. And if you realize that my 5 newton vector is to the left, then it's negative 5, right? So it's negative 5 minus positive 2 newtons. And what is negative 5 minus 2? That gives me negative 5 minus 2 is negative 7 newtons, right? Hold on, just a little blunt. Oh, okay, sorry, just made a mistake here. Okay, so this had to be 2 newtons minus negative 5 newtons. And that would actually give me, that's 2 plus 5, that gives me 7 newtons, right? There's actually something going on here. Let me see. Oh, okay. Just a little mistake. Ah, silly me. Okay, so remember we say that vectors in the opposite direction are subtracted, right? So think about it. So if I say that vectors, well, we're talking about the addition of vectors, right? In order to get me to my resultant. Now let's just discuss the word resultant in general. When we talk about something resultant or net, we are talking about the total, right? So if I talk about the total, that means if I want to talk about the total profit I made, that's some profit plus some other profit plus some other profit plus some other profit. That gives me the total profit. Similarly, the net vector or the total vector would be some vector plus some vector, right? So it would be negative 5 newtons plus 2 newtons, and that gives me a negative 3 newtons. And you notice that a negative 3 newtons is negative. So that's in essence 3 newtons. Look at the sign, negative, tells me that it's 3 newtons to the left or west, right? So it's 3 newtons to the left or west, okay? And now, okay, so we've looked at 3 newtons to the left. Now, another thing that you would actually look at, I mean, another way in which you could get this is this. Your resultant vector will take the direction of the longest vector, okay? I mean, it's fairly easy with these two. I mean, it becomes a bit more drastic when you have more than 3 vectors just acting, and it's just a lot of calculations. It's an entire hullabaloo. But in essence, you just take the direction of your resultant vector will be in the direction of your largest vector. So notice here you had your largest vector, which is 5 newtons to the left, meaning your resultant vector will be 3 newtons to the left, right? So it's just another different example. I want you to see something. So let's look at another one. Say I've got a 12 Newton vector, and the opposite direction I have a 7 Newton vector. So notice something. I drew it straight from the head of the first vector. So that's the direction to the right, and that's also to the right. So how do I determine my net vector? Remember, that's 12 newtons plus negative 7 newtons. Why? Because it was 7 to the left, and we did say that we are taking right as positive. Okay? So anything to the left is negative. So that's 12 newtons minus 7 newtons, and that gives me 5 newtons. Yeah. Now, again, what is the direction of this guy? Is it 5 newtons to the right or to the left? You look at your largest vector, which happens to be 12 newtons. So that is 5 newtons to the right. Or similarly, you could just also look at the sign. Remember, right is positive and my sign is positive here. So that just does actually confirm that it's 5 newtons to the right. Okay, coolios. When it comes, I've noticed that I've been actually including my ends in my calculations. That is not necessary. Just please don't forget that. It is not necessary for me to keep saying 12 newtons, 7 newtons within my calculations. I can just say 12 minus 7. What is important is that my final answer has newtons as well as my direction. Because if you just have 5 right, I mean, what's 5 right? 5 right. What is that? That's like, okay, cool. That's a number and that's the direction. So it's 5 right. I mean, you can expect to get marks for something like that. So it's very important for you to indicate your direction as well as your SI unit. Okay. So we've looked at the addition and the subtraction of vectors, right? So suppose you had a combination of vectors. It's just an entire hullabaloo of vector system. Let's say you have a vector in that direction, and that's 5 newtons, and you have another one in that direction, and that's a 4 newtons. And oh, and by the way, you'd notice how I'm just drawing these vectors by hand. I would prefer that in an exam you use a ruler, right? So in your ruler, you could have this type of scale. You could say, for example, 1 centimeter is equal to 1 Newton, right? Meaning, so 2 centimeters on your ruler would basically be 2 Newtons. So you'd have your, I don't really have mine here. Um, in fact, I do have one here, just not on the screen. So I'm just going to use that, right? So I would have 1 centimeter is equivalent to 1 Newton. So if I have to draw my vector of 5 Newtons, I'll draw my vector of 5 centimeters. So I would start here, and just to position my ruler, and I would start at 0. Okay, start at 0, and I'd say, okay, so that's 0 all the way. Okay, that's just all the way to 5. Okay, there we go. So that would be my 5 Newton vector. By the way, I used the ruler on this, so it's like 5 Newtons to the right. And then say you wanted to have 7 Newtons to the left, you'd start at the head of 5, remember, and you'd place your ruler from the head of 5 at the 0 mark and just go 7 centimeters to the left, right? So you'd have something like this. Okay. So just from the head, from the head, okay, and you would go that way, and that would be my 7, sorry, that's 7 Newtons, right? So just make sure that you use your ruler. Remember, 1 centimeter is equivalent to 1 Newton, right? So if I have 7 Newtons, that means it was basically on my ruler, I had 7 centimeters. Okay, cool. So we have that, and let's say we add another vector. So I'm just going to continue with my rough hand, but please make sure that you actually use a ruler, because with a ruler on my side, it could take decades, but it should be quick on your side. Okay, so from here, let's just add another 3 Newtons. Okay, and then we add another. Okay, let me just. Okay, let's add another 2 Newtons. Okay, and when we are required to determine the resultant vector. Okay. Cool. So if I had to draw the resultant vector, I would then say, sorry, if I had to that's a bit of a tongue twister. If I had to determine my resultant vector, then I would have something like this. Now, focus on this. So you have 5 Newtons and 3 Newtons in the same direction. So that tells me I need to add those two. I would then say 5 Newtons plus 3 Newtons. Remember, the sign remains positive because it's the addition of the two. Oh, sorry, I don't know why I have this all the time. So that's just 5 plus 3 plus. Now notice something. These two guys over here are to the opposite direction, right? But because they're in the same direction with each other, they actually add each other. So you'd have something like plus, right? 7 plus 2. And that would be 8 plus 9. But remember something. This 9 was the sum of the guys in the opposite direction. So I need to say 8 plus negative 9. And that would give me, sorry, what's 8? Oh, sorry, a negative 1 Newtons. But because it's negative 1, you chose right as positive. That tells you that it's 1 Newton to, sorry, almost said right, to the left. Okay, I mean, if this was a bit confusing, you could have thought of it this way, just, you know. So you could have said, because 7 is in the opposite direction as 5 and 3, I could say negative 7 minus 2, right? Because it's negative 7 plus minus 2, which is just negative 7 minus 2, and that would still have given me negative 9, right? And then I would still get my answer of 1 Newton to the left. And you notice something. My biggest vector is to the left, and that is my 7 Newton vector. Hence, my final answer is 1 Newton to the left. Really hope you guys are seeing that. Remember, the direction of the resultant vector is going to be the same as the direction of the largest single vector. Okay. I think that just about covers everything. Okay, I think just before I go on, before I conclude, just look at naming vectors. You know, sometimes it not that it's necessary, but we could say this was force vector 1, force 1, and this would be force 2, and this would be so that's oof, oh, a little bit of a blunder right there. Okay, this would be force 3, and this would be force 4. And then obviously to answer your questions, all you would do is just say so that's force 1 plus force 2 plus force 3 plus force 4. And that would be that right there. Okay, cool. So what you also need to know is that your vectors can be represented in different ways, right? So they're like a vector in the exam, you could get a Cartesian plane. You remember the Cartesian plane for mathematics, okay? So you have different methods of representation. So you have your different methods of representation, right? So you'd have it on a Cartesian plane. So it's my Cartesian plane, okay? Okay, so in my Cartesian plane, I would have something of this, right? I would have a vector in that way. Okay, why did I not change my color? Okay, there we go. In fact, no, that was actually 5, but anyway. So I'd have my vector in that way, right? And I would have another one probably in that direction. And, sorry, and another one probably in that direction, right? And let's just say this was force F1, and that was equal to 10 newtons, and this was force F3 equals to 6 newtons, and this was force F2 equals to, say, 4 newtons, right? Now, how would I actually read this, right? And you'd obviously get your angles right here. You would get what we call the angle of incline. So let's say that particular angle of incline was 30 degrees, and another one here would be say 20 degrees, and this one right here would be 10 degrees, right? So I would have F1, F2. So sorry for the noise. So I'd have F1, F2, and F3, right? So you notice something. We have this angle right there. That angle we call the angle of incline, right? So it is the angle between the diagonal and the horizontal axis. It's just the angle right there. I mean, even if I have my thing like this, that's between the diagonal and the horizontal right there. I mean, even if I have it like this, that's the angle between the diagonal and the horizontal, right? So what we call the angle of inclination. Okay, coolios. So that's how you would actually have it on a Cartesian plane, right? And that's obviously with this one, F1, you could say F1 is 10 newtons above the positive x-axis, right? And F2 is 4 newtons below the positive x-axis. Or you could say that the 4 newton is F2 is 4 newtons to the right of the negative y-axis, right? So it's 4 newtons to the right of the negative y-axis. And you could say F3 is 6 newtons above the negative x-axis, or to the right, or rather to the left of the positive y-axis. Okay, cool. So you would have this first method, and we would have the second one, which we call the compass. You know, it's like a almost similar to this one, right? And this one would also give you a Cartesian plane. And on the Cartesian plane, you would have your typical drawings. Let's just make that 10 newtons again. That's 10 newtons, and that's F1. Let's just have that right there. Just gonna make that a bit bigger. Let's make that 11 newtons, and that's F3. Come back down here, and that's 5 newtons, and that's F2. Okay, so what you would actually have here, oh sorry, just I forgot the angle, so that's 30. Let's take this up a notch, let's make it 15. So down a notch. And let's take this up a notch and make it 20. Okay. Remember the angle of inclination. Okay. Now this is what we call the compass. We call this the compass. And we call this first one on a plane. That's just on a plane or a certain graph. So it's on a plane or on a graph. Okay. Now we have this. So how would we actually read this? So to read this guy right here, we would say that is 11 newtons above the negative x-axis, right? And this guy, the 10 Newton one would be, sorry, just the equal sign, right? For 10 newtons would be 10 newtons above the positive y-axis, right? That's how you would say it in the first one. But in this second one, it's a bit different. So in the second one, you'd say, this is 11 newtons to the north of east. Sorry, to the north of west, my bad. So it is 11 newtons to the north of west. And this is 10 newtons to the north of east. And this guy is 5 newtons to the south of east. South of east, very important. Okay, now you realize that I'm actually having these as south of east, just a very important NB. The only time I am allowed to say this is 5 newtons, for example, southeast, I can only say that if and only if the angle of inclination is 45 degrees. That is the only time I am allowed to say southeast. But if I have any other angle that is not equivalent to 45 degrees, this guy will not apply. So instead of writing southeast, I'd write south of east if my angle is not 45 degrees. Okay. That is a very important point. But anyway, so what have we looked at? We have looked at vectors and scalars. We've looked at different types of vectors, different types of scalars. We've looked at the graphical representations, how to actually draw a vector. We've looked at the important part of direction of convention, right as positive. We looked at different ways in which you add and subtract vectors. We've looked at the resultant vector. Oh, and just a quick thing, look at this thing. Remember, when I said that a resultant vector is larger when the vectors are in the same direction. So let's just look at this one. Look at the first one. When you have vectors in the same direction, you have your resultant vector as 7 newtons. But with vectors in the opposite direction, you should have it smaller. So look at your resultant vector. Here, I still had 5 and 2 in the opposite direction, and I got 3 newtons, which actually shows that 3 is less than 7. Okay. This is just the point I wanted to raise. And we have covered all of these in this video. So in the next video, we'll be looking at motion in 1 dimension. But from me to you, thank you very much for tuning in, and I will see you in the next video.